If you're interested in learning about particle physics, one of the key topics you need to understand are the forces that come into play. For instance, we know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Of these 4, we have at least a little familiarity with gravity and electromagnetism, so naturally, I want to tell you something about the strong nuclear force. The first question you might want to know the answer to is, how do we know that there's a strong nuclear force at all? Well, this is something we've known for essentially a century. In 1911, Ernest Rutherford discovered the basic structure of the atom, which is that it consists of a small and dense core of positive electric charge called the nucleus, surrounded by a cloud of negatively charged electrons. And in 1917, he discovered the proton, which meant that the nucleus consisted not of a big blob of electric charge, but of a whole bunch of smaller blobs held together. Remember that each proton can be imagined as a tiny ball with a positive electrical charge. They say that opposites attract, and that might well work for couples, but it's definitely true for electrically charged particles. On the other hand, like charges repel each other. So let's imagine a simple nucleus consisting of just 2 protons. Since each proton has a positive electrical charge, they push each other apart. And they don't push each other apart a little bit. The repulsion force is about 20 pounds. 20 pounds is a respectable force in the world of you and me. In the particle world, it's huge. It's so big that if you let the 2 protons go, they'd push until they were moving away from one another at a speed of over 8,000 miles per second. And I just picked the simple case of 2 protons. In the case of uranium, there are 92 protons all packed together in a ridiculously tiny volume, and a proton on the surface is repelled with a force of just over 70 pounds. So, if these protons are all getting pushed apart from one another, what keeps them together? There's only one possibility. There has to be a force that is even stronger that counteracts the electromagnetic repulsion. And the name for that force is, you got it, the strong force. What do we know about the strong force? Well, we know that it's strong, and it can't just be a little stronger than the electromagnetic force. That's because if the 2 forces were pretty similar, it would be easy to knock protons out of the nucleus of atoms. And we know that's not true because nuclei last for millions and even billions of years. So the strong force has to be way stronger. From tests, we know that the strong force is about 100 times stronger than the electromagnetic force. But the story is a bit trickier than that. After all, if the force is so high, what keeps the strong force from continuing to gather protons until the whole universe consists of one big nucleus? If we look at the periodic table, we see that the highest stable element has no more than about 100 protons in it. And yes, I know that the nuclei also contains neutrons. That doesn't change much in what we're talking about here. So it seems that with more than about 100 protons, the strong force can't hold it all together. What's that all about? It turns out that there is a property of the strong force that is quite different than the electromagnetic force. Electromagnetism has an infinite range. In principle, 2 electrically charged particles will feel a force between them if they're separated by the entire universe. Okay, the force would be small, but in principle, it's true. In contrast, the strong force is more like a contact force. When 2 protons touch each other, they feel the strong force. Pull them apart a little bit, and the strong force goes to 0. In a way, the strong force is a little like Velcro. When 2 pieces of Velcro aren't touching, the 2 pieces feel no force toward one another. So that's the strong force. It is stronger than the electromagnetic force, but it has a much shorter range. And those 2 properties explain why low-mass nuclei are stable and heavy ones aren't. In the heavy ones, all the protons in the nucleus push against all the other protons, while the strong force only feels the force of its neighbors. And this is all pretty cool. What I've told you here is actually nuclear physics, not particle physics. I'll make another video that brings the strong force into the particle world. The strong force is a fascinating subject, and it is the strongest known force in the universe. Well, the second strongest force.